My name is Catherine Roberts. I'm the Executive Director of the American Mathematical Society, and I'm pleased to be chairing today's session. This is an invited session. We've had 4 lectures today. We're about to have the 4th here. This is section 15 and 17. 15 is for numerical analysis and scientific computing, and 17 is for mathematics and science and technology. Our last speaker today is Shi Jin. He's the Vilas Distinguished Achievement Professor in Mathematics at the University of Wisconsin in Madison, United States. He's also Shunchen Chair Professor at Shanghai Jiao Tong University in China. Shi Jin's PhD is from the University of Arizona in Applied Mathematics with David Livermore. He works in numerical analysis, partial differential equations, kinetic theory, quantum dynamics, and uncertainty quantification. And today, Professor Jin's talk is mathematical analysis and numerical methods for multiscale kinetic equations with uncertainties.
Thank you, Catherine. And I'd like to thank the program committee and the panels for giving me this honor to speak here. So today I'm going to talk about some recent work that I've been doing with my colleagues and students on the subject of uncertainty quantification for kinetic series and also multiscales. All right, so first just to show you where kinetic series sits in the description of multiscale physics. Here, if you start with a very microscopic scale in both space and time, you have this quantum mechanics. The next level is molecular dynamics. We have heard a few talks today on continuum theory, for example, fluid dynamics. And between the molecular dynamics and Newton's second law and the continuum mechanics, there's a scale in between, usually called the mesoscopic scale, which is a so-called kinetic theory. And the most fundamental equations for kinetic theory is Boltzmann equation. And apparently, if you simulate at different scales, you have to use these different physics. If you simulate n-body Schrodinger equation or n-body Newton's second law, it's usually called a first principle simulation, where you have this equation with Coulomb interaction, there's no parameters, and then if you can able to do it, and you understand everything about the physics, about the matters. However, we know that simulation at this scale is impossible by today's computer. So you have to go beyond this level, and then at these levels, you start to introduce empirical formulas, relations, and data. So uncertainty becomes inevitable. Of course, what I said even at this level is not true because we are unable to solve for example, n-body Schrodinger. You still have to use things like field theory, like Hartree-Fock theory, density function theory. At those levels, you also have uncertainties. So essentially, uncertainties at all different levels. But I'm going to concentrate on this level. And of course, there are a lot of applications with kinetic theories from the classical application in ratified gas dynamics. If you want to do space shuttle reentry, you have to solve Boltzmann equation, then in plasma and many other areas. And more recently, there are a lot of new applications in environmental science, solar energy, in social science, neural network, and so on. And this big research network it's called KNet, sponsored by NSF in US. Adam Telmo is the PI of that grant. So there are a lot of activities. It's a very lively area in kinetic theory. This is my summary of the computational challenges for kinetic modeling and simulation. The first one is high dimension because kinetic theory describes particle distributions in the phase space. So it's already 6 dimension compared to 3-dimensional fluid dynamics. You already have dimension curves at that level. And there's also multiple scales because typically the Newton's number can change in several orders of magnitude in one computational domain. But these two classical computations are kind of classical, is well known, there has been a lot of work. The third one is what I call uncertainty, which is a sort of unexplored area. I don't know why, but that was the fact. So this, talk about a multiscale, this is a slide that I stole from this talk. Well, if you want, for example, if you simulate nuclear reactors, there are different physical levels you can do it. which usually have to solve a neutron transport, but you may also need to solve, for example, coupled with fluid dynamics and heat transfer. So these are naturally multi-physics, multi-scale problems. And about uncertainty, the reason kinetic equations in kinetic modeling uncertainty is inevitable is because if you look how kinetic equations are derived, usually you start with unbodied Newton's second law. That's the first principle, all right, and no free parameters. And you start to take so-called mean field limit using, for example, BBGKY hierarchy, and they have to truncate. And well, in the case of Boltzmann, that's known as Grad-Boltzmann limit. But even for Boltzmann equation, that's one of the fundamental equations in physics. It's kind of crude approximation because they have to assume this special relation between the number of particles and the size of particles. It has to be satisfy certain scaling in order to even derive a Boltzmann equation. So it's sort of crude. And very often the collision kernels are empirical. You cannot write down an analytic formula for the collision kernel, which is an important coefficient in the Boltzmann equation. And also, there's also initial boundary data because Boltzmann equations solve a particle probability density function, which is not a physically measurable quantities. And we even don't know what is the right boundary condition to solve a kinetic equation very often. You don't know what the boundary conditions are. Then there's also other errors, for example, geometry forcing term. Of course, the UQ has been very popular in the last 2 decades. There's a SIAM annual meeting and new journals and so on, and has been worked in many different areas. But I mean, if you look at the literature, there's almost nothing was done for kinetic equations, which is a little bit strange, considering how important kinetic theories are. If you look at my first slide, you see that it's one of the most fundamental equations in physics. But there hasn't been anything done until very recently. So this is the example where you see that this is the modeling of neutron transport neutron scattering. And this scattering coefficient, there's no analytic formula, so there's a big device in place like Los Alamos where there's a big experiment to measure this scattering coefficient. So these are different curves depending on different periods of simulation from the 50s to the 80s. So it depends on the precision of the measuring, they get different curves. So apparently these are data which there's no formula. So there are a lot of uncertainties depending on how accurate your measurement is for a scattering coefficient in the neutron transport equation. All right, so what do you do if you want to do a so-called uncertainty quantification? There are many things you do, and in my opinion, actually, for kinetic models, the only thing certain is their uncertainty. All right? So you can do a lot of things when you have uncertainty. For example, you want to quantify the propagation of uncertainty. You want to develop efficient numerical methods to study the uncertainty, and you want to understand the statistical moments, and you want to conduct sensitivity analysis because very often you have many source of uncertainties, and you want to make sure some of the uncertainty parameters are not important, not sensitive, you can throw it away, but other parameters may be important, you have to keep it in the model. And you also want to understand the long-time behavior of the uncertainty. And also, there's a lot of control problem, inverse problem to solve. You want to control the uncertainty to obtain desired output, for example. And very often, uncertainty quantities also appear in very high dimensions, so there's a big challenge how to reduce dimension. So there are many questions you can try to study. And this example, which shows that uncertainty, you should be careful with uncertainty. It's a simulation of Boltzmann, but with a small Newton number. So this is a standard shock tube problem. So I saw a Boltzmann equation with a shock tube, which usually you see this in shock capturing problem. So this is standard shock tube problem with the Newton number, I forgot it's 10 to the minus 6. So these are the kind of picture you see in a typical solution for Euler with Riemann problem. So you have that. This is density, you have a 3 piecewise constant connected by refraction, contact discount, and shock. So these are velocity. This is the heat flux. So these are expected value of this problem. So I perturb this initial density by Z is a uniform distribution between -1 and 1. So you perturb this Riemann data by some uniform distribution. Then the average value, of course, looks like what you have if you have been doing shock capturing. This is the standard picture you see. In average, nothing happens, no surprise. But if you look at the standard deviation, then you see there's a big deviation near the shock. All right, this is a heat flux. So if you want to design an airplane or a space shuttle, you have to make sure the material of your vehicle can survive such a big deviation of heat flux, because you don't want your vehicle to burn, right? So clearly the deviation is something you worry about. Not only you have to worry about the average, which looks like okay, but the deviation is something you worry about. And this uncertainty quantification actually allow you to understand all this statistical behavior when you have a random perturbation. All right. Of course, if you model a random field, very often used approximation is so-called Collisional lobe expansion, where by this expansion, any stochastic process can be approximated by a linear combination of uncorrelated random variables. So our modeling of uncertainty will actually start from here. Basically, we model uncertainty by random inputs in the coefficients or initial boundary data or forcing terms. All right. So these models usually appear in the form of random PDEs. And a classic way to solve a random stochastic PDE is to Monte Carlo, which works very well, especially in very high dimension, but it suffers from low order of accuracy. We know Monte Carlo is only half order convergent. And in the last 2 decades, there are some other more better method which has been developed. One is so-called polynomial chaos approximation, which was first introduced by Vienna in the 40s, where he wanted to study Berger's turbulence. And in the last 2 decades has been formulated into a mathematically very competitive methods. Has been very popularly used in many UQ applications. And of course, the constraint of this method is that it's basically a spectral method. You want a solution has sufficient regularity in the random space, all right? So the way this method works is that suppose you have a Z, use this Z as a random variable, and use Z to model a random input. So assume Z is a random variable with a given PDF, and then it's a basic numerical analysis that you can use this PDF omega as a weight function. Then you can construct a family of orthogonal polynomials denoted by phi I. So phi I is polynomial degree I, so it's also normal with the weight omega, all right? So it turns out for different random variable, there's also always a corresponding family of orthogonal polynomials. For example, if you have a Gaussian random variable, the polynomial is Hermite. If it's uniform distribution, it's a Legendre polynomial. There's similar correspondence for discrete random variables. And the way this works now, once you have this orthogonal polynomial, and they actually span, it's a basis for L2 space. So for any L2 function that depends on this Z, you can write as a linear combination of this basis function, where this Fj is a inner product of F with phi I. So Fj does not depend on Z. So numerically, of course, you truncate as some finite degree of polynomial k. And this is your numerical approximation, Fk. Then you just plug in these ansatz into your PDE and you do Galerkin projection. Then you end up at the system equation for this coefficient, And this now you get a new system of PDE, which is actually deterministic. All right? So you solve the deterministic equation for this coefficient. And once you have this coefficient, that gives you all the statistical moments. For example, now the expected value of this guy is nothing but the first coefficient. That gives you expected value. And the square sum of all the other coefficients from m, what should be 1 here is typo, from 1 to m. The summation of this gives you the variance of fk. So I mean, once you have this solution, solving this DD for this coefficient, you get all these statistical moments. So this method is called a stochastic Galerkin method, all right? And it's like spectral method because it's an expansion based on orthogonal polynomial. It's like a spectral method. So if you have a good regularity, then it has a spectral accuracy. So it certainly beats Monte Carlo, which is half order. Of course, to make sure this method is really good, you have to do regularity analysis, which is what we are going to do. I mean, of course, we're going to do, here we talk about stochastic Galerkin, but our regularity analysis also is important for other methods, which, for example, stochastic Galerkin. And Stochastic Galerkin is so-called intrusive method where you have to solve a new set of PDEs. But the collocation actually you can still use legacy code. But our analysis, of course, is important for all these different methods. Well, then there's also issue of how do you deal with multiscales when you have a kinetic modeling. So for multiscale, there has been a methodology which has been introduced since in the last 20 years, has been very popular in the multiscale kinetic community, so-called asymptotic preserving methods. So this diagram shows you what it means. So suppose you have a dynamic system which depends on some possibly small parameter epsilon. In the case of kinetic equation, epsilon is a Newton's number. Okay, it's a mean-free path essentially. So this is, for example, it's kinetic model. When the Newton's number goes to 0, you arrive at a hydrodynamic model, Euler equation, for example. All right. So epsilon can be order 1. That is kinetic regime. If epsilon small, it's a fluid regime. Now, if you discretize this f, then you introduce the numerical parameter delta. And typically, delta has to be smaller than epsilon, then you get a numeric convergence, all right? But of course, if you cannot afford to do a fine simulation, if your numeric parameter delta is larger than epsilon, then the classical numeric analysis does not give you the right information. What you need to do is, now you know how to derive a macroscopic model from microscopic one by taking asymptotic analysis. Now you do the same asymptotic analysis at discrete level by fixing delta and let epsilon go to 0. Then you end up at a scheme which no longer depends on epsilon. If that scheme turns out to be a good scheme for this macroscopic model, then we say this scheme is asymptotic preserving. Basically, asymptotic preserving mimic the asymptotic transition from microscopic to macroscopic model at the discrete level. All right? So essentially, you have a kinetic approximation. When epsilon goes to 0, it automatically becomes some nice fluid solver. So that's called asymptotic preserving. So this kind of scheme allows you choose delta not independent of epsilon. It works in for both small epsilon and large epsilon. So this method has been very popular. Was introduced in the 90s. It has been very popular in the last 20 years in the kinetic community. All right. And now, of course, you have stochastic PDE. We try to extend this AP method. The idea is following. So now if you have a dynamic system which depends on both small scale epsilon and this random variable z, all right? So we can extend this AP idea to stochastic setting by using it with stochastic Galerkin. So the idea is that, okay, this dynamic system is a microscopic model, random. When you go to 0, it converges to some macroscopic model, which is still random, depending on z. Now, if you have a stochastic Galerkin method for this equation, by fixing the polynomial order, you pass to the limit. When you go to 0, if you end up at a stochastic Galerkin for this limited system, that we call it stochastic Galerkin. All right. And this picture shows you what it means. So you have an uncertain kinetic model. When you go to 0, you get some uncertain fluid model. So this is a microscopic model, this is a macroscopic model. Now you discretize it by stochastic Galerkin method with a polynomial degree up to k. All right? So at this level, you get a deterministic system. And once you have a deterministic system, then we can use this AP machinery that has been developed in the last 20 years for deterministic kinetic equations. Then you derive a scheme which actually allow you to take limit, either take epsilon 0 limit first, or you take all the numeric parameter 0 first, and this limit commutes. So that's what the stochastic AP means, all right? So the idea is that once you use stochastic Galerkin, then everything deterministic, then you can use deterministic AP machinery to solve this stochastic problem. So that's the idea. So now I give you a specific example to show how you can do it. So this is a simple linear neutron transport equation. I joint work with Dongbing Xu and Xue Yizhu. So the F is the probability density distribution of neutron. In this problem, the neutron will collide with the background media, which is nuclei. So the right-hand side is a non-local operator, but it's linear. because of the interaction between nuclei, between neutron and the background. So this left-hand side is the convection. So the particle that has a velocity, and here actually is the angle, cosine angle of the velocity with the x-axis. So I just misused the notation. I just called it velocity. So left-hand side is just transport, linear transport. Right-hand side is collision. So this is the loss due to the collision, and this is the gain due to this is scattering collision. So it's a non-local operator. All right. So sigma is the scattering coefficient. Well, that's the remember I had this data, computational data. That's the sigma. All right. So the sigma clearly depends on x, but it may also depend on uncertainty. So epsilon is the Knudsen number. All right. To make an asymptotic limit interesting, you have to rescale to a long time. So this actually, if you fix z, if you take any random sample z, and this is a classical problem where people know that if you send epsilon 0, then the macroscopic density, which is this velocity average of f, if you denote this rho to be the velocity average of f, then when epsilon goes to 0, actually it's rho, solve the diffusion equation. So this is from non-local to local, all right? A non-local operator becomes a local operator in the limit. That's what Chang Du was talking about. But this is a physical model. It's not an artificial non-local model. All right? So this classical analysis on this for deterministic problem, of course, nobody did anything if sigma is random. So now, the different way for fixed z, this deterministic kinetic equation, I mean, there has been a lot of methods that has the AP property. So here I give one example, is to use so-called even, you split the equation according to a positive v. Here v is the cosine of the angle, so it's between -1 and 1. So if v is positive, you just copy the equation. If v is negative, you put the minus. So then you have to solve these two equations with only v positive. Then you do a linear combination. If you add these two equations, you call that's an even function in v, called the r. This is the odd function, you call it j. So that's the density. This is essentially the flux. Then you can write the equation for r and j, which looks like this. All right. And then from here, you can see that you can, so this is the coupled hyperbolic equation. For fixed v, this is a linear hyperbolic equation. The right-hand side is non-local because it's r bar is the, you integrate all over v from 0 to 1. All right. So from here, you can see diffusion limit very easily because when you don't go to 0, and from the second equation, you get j is essentially the r derivative divided by sigma. That's the leading order. This is like Darcy's law, actually. So J, flux, is the gradient of temperature in the case of Darcy's law. I have the sigma over here. Now if you plug this relation to the first equation, you integrate over v. Then you get integrate over v, the right-hand side is 0 because it's r. Integrate on this, you get r bar minus r bar. And then you get r bar actually is exactly the diffusion equation, where diffusion coefficient is a reciprocal of the scattering coefficient. All right. All right, so now, for every fixed z, this is like a deterministic kinetic equation. Now if you solve this using a deterministic AP scheme, and then you can generate, so now the idea is that I might start from this equation, and this formulation allows us to design AP scheme very easily. So now you just use this stochastic Galerkin ansatz for both r and j. You stop at the polynomial degree m, and then you throw in this ansatz into this r and j equation, and you do Galerkin projection. Then you get a system for this coefficient r, and I denote it by a vector. So now you compare this equation with the previous equation, and looks completely identical, except now it's vectorized. All right, still r and j, but it's a vector. And then the idea is that, but of course, before it's a scalar, here you have vector, and before we have sigma here, but now we have this matrix S, which is connected to sigma, sigma times this basis function. Well, this should be omega, by the way. So it turns out this S is a nice matrix. Actually, sigma is always positive, so S is positive, definite, symmetric. So S, you can invert S. Now from here, you can see that it's actually AP because when epsilon goes to 0, J is S inverse times the derivative R. If you plug that into the first equation and integrate over V, you get actually a stochastic Galerkin for the limiting diffusion equation. You can easily check that. All right? So what's nice about this looks like the original equation, looks like deterministic kinetic equation, so you can use deterministic AP scheme to solve that. So for that reason, actually it's just a vector form. So people don't like stochastic Galerkin because they call it's intrusive. I call it semi-intrusive because it's essentially the same code as the deterministic one, except you have the vectorized. Before you have scalar, now it's vector. Of course, here you have a matrix. So you only probably spend half of the day to use your legacy code. So I call it semi-intrusive. It's not too bad, all right? So now why is stochastic AP? Because as I said, if you send it equal to 0, actually the stochastic Galerkin for the transport equation automatically becomes stochastic Galerkin for diffusion equation. So this means that actually you can choose parameter, this k, polynomial degree, independent of epsilon. And actually we have some rigorous theory for this method. It's joint work with Jian Liu at Duke, and Jiang Ma is my former PhD student at SJTU, is now postdoc at Purdue. So the idea is that now we can use this weighted L2 or subleft norm. So omega is PDF of a random variable z. You take a weighted inner product. This is the corresponding subleft norm. So you take half derivative on z, and you add, is weighted with omega. So that's the standard weighted subleft norm. And the idea here, the keyword is so-called hypocoercivity. I will elaborate a little bit more later. So then if I take case derivative on the z variable, and we can prove actually the regularity of the solution in the random space is uniform in epsilon. So this is a theorem. If you assume this scatter coefficient is strictly positive, all right, for any z. And the story here is that actually the transport equation preserves the regularity of the initial data and also the coefficient sigma. Okay, it has same regularity as the initial data f0 and also this coefficient sigma. And also this bound, the subleft norm up to m's derivative in z is uniform bound in epsilon, and this bound, which makes it the problem a very nice problem for UQ and also for stochastic Galerkin method. But actually also for a good method, it's really good for also stochastic collocation because you have this nice regularity, all right? So essentially the regularity of the initial data coefficient is preserved in time in the random space. Of course, to prove this, you have to, here is what I mean hypocoercivity. We do energy estimate. Usually if it's a hit equation, you take a subleft norm, and the left-hand side is something negative times the same subleft norm. But here, here you have f, but here is f minus bracket f, where bracket f is the velocity average. So the right-hand side is not f, so you do not immediately get the exponential decay estimate. And instead, you have to do a little bit more careful analysis. You have to also measure the f from its deviation from local equilibrium. You estimate this one, and then you see this will have exponential decay from the initial data, plus all the epsilon square term, which is the modeling error. So the epsilon square is actually the deviation of transport from the diffusion, all right? Now if you combine this estimate, then you can prove that if sigma is strictly positive, then essentially, if the initial data is a subleft norm in the random space up to hm, then the distance between analytic solution and your stochastic Galerkin approximation up to polynomial degree k is bounded by capital K, polynomial degree to little k, which is subleft regularity. And this constant now depends on the final time, but independent of epsilon. This shows you that if you do polynomial calcs, now k can be chosen independent of epsilon. All right, that's what we call the stochastic AP. And if you take full discrete scheme, and now everything's deterministic, and you can use deterministic AP, for example, something for the micro-macro decomposition. Actually, we can prove that for the fully discrete scheme, the time step is bounded by delta x squared plus something that depends on epsilon. But when epsilon goes to 0, of course, delta t as a uniform lower bound. Actually, get the CFL condition, which is what you get for solving a hit equation anyway, when epsilon goes to 0. So that delta t does not go to 0 when epsilon goes to 0. So essentially, you can choose all numerical parameters independent of epsilon. in this framework. So here's some numerical example where we basically, epsilon is 10 to the minus 8, and we choose the polynomial chaos order from 0, 1, 2, 3, 4, and you can see a very quick decay as you increase the degree of polynomial. All right, it's exponential decay. Of course, it's saturated because now once you're here, you have numerical error from delta x and delta t. So here I choose delta x and delta t to be 10 to the minus 2, although epsilon 10 to the minus 8. And this shows you that now I fix all the numeric parameters, all right? So polynomial degree is, let's see what it is. I think polynomial degree is 5, something like that, fourth order polynomial. And delta x, delta t are all 10 to the minus 2. I shrink epsilon from order 1 to 10 to the minus 8. And you see a linear decay in epsilon. So this shows that the method actually, AP method, converges in epsilon, all right? Essentially, of course, it's saturated here because once you are here, the numerical error from delta x, delta t dominate. You no longer improve. But in this large part, you see linear decay in epsilon. And this example shows you that for epsilon equal 10 to the minus 8, I use fifth order polynomial chaos, and the random dimension is 2, and delta x, delta t is ordered 10 to the minus 2. You still compare with the refined calculation used the collocation, you get a nice agreement. So with this combination is highly under-resolved. Epsilon 10 to the minus 2, mesh size 10 to the minus, epsilon 10 to the minus 8, but mesh size 10 to the minus 2. All right, so that's the story about the linear transport equation. And it turns out actually we have a rather complete theory for essentially all classical kinetics equations. Jordan works with Liu Liu, a former PhD student who is now a postdoc at UT Austin. So it turns out that we have a rather complete theory for nonlinear collisional kinetic equations using so-called hypocoercivity theory, which is a very well-established theory in kinetic community. Villani, and in his field method work, he used heavily hypocoercivity. So this has been a lot of work for hypocoercivity in the velocity space, and that gives you a lot of beautiful results. It turns out we can extend this theory to the random space, which allow us to get a lot of very good results. For example, for regularity. All these results are in random space. Regularity, also sensitivities in random parameters, and also long-time behavior. We can prove an exponential solution in the random space. We decay exponentially to the global equilibrium. And it also allows us to do numerical analysis. For example, with this hypocoercivity theory, we can prove stochastic Galerkin method has a spectral convergence and even long time exponential decay of the error. We know, numerical analysis for a long time is very difficult. Not many frameworks allow you to do long time analysis. Well, symplectic method is one of them, but not many. Usually get e to the something positive times time. But this method actually allows us to get long time exponential decay of a numerical error. All right. So there's some also relevant contributions with another two PhD students, Yuhua Zhu and Raven Xu. And also for the linear problem, actually, Qing Li and Li Wang did the similar work. This example to show you what hypocoercivity means. If you solve heat equation and you plot its entropy, you get exponential decay, like that. Simple energy estimate. Hypocoercivity actually is like a staircase. You don't get a uniform decay. You get a staircase. Of course, the Boltzmann actually is more difficult. It's like this. And of course, if you can prove this, you get fused metal. That's what one of the work that awarded Villani fused metal. There's another work he has two work. Another one is Landau damping. So you need to have to prove something. This guy decay in the long time. We are dealing with this case, all right? So that's the so-called hypocoercivity. And it's very difficult to prove it. We want to prove it's uniform exponential decay. This guy decay, but you want to prove under certain norm, it decays uniformly in time. So that's something we want to get. So the idea, so I'm going to do it for the general collisional kinetic equations. We follow basically deterministic work by Mohor, and Brown was a former PhD student. The idea is to create a general class of collisional kinetic equation. So this is transport, this is collision, which can be Boltzmann, Landau, and many different kinetics. Now we assume the initial data depend on this random parameter z, all right? So here we have alpha, epsilon is Newton's number, alpha, different alpha corresponding to different regime. If alpha equals 1, it's called the incomplete. Then you take epsilon to the 0 limit, you get the incomplete Navier-Stokes scaling. If alpha equals 0, it's called Euler scaling. But in our case, I would rather call it acoustic scaling. And we consider periodic boundary condition. That can be generalized to general infinite space. So the main idea for this hypocoercivity is use a perturbative setting, all right? So you essentially assume F is this global Maxwellian, which is deterministic plus fluctuation. And so you plug this into your kinetic equation, then you get equation for this fluctuation H, which left-hand side looks the same. Now the right-hand side has two parts. The first part is a linearized operator, L, linearized around this global Maxwellian, which is e to the minus v squared over 2. You normalize it, all right? These are the nonlinear departure from this linearity. All right? And why the perturbative setting works? The reason is that for the linear kinetic equations, you have this hypocoercivity. And if you look at this ratio, I mean the exponent of epsilon, here there's always one actual epsilon compared to the linear part has actual 1 of epsilon compared to the nonlinear part. So the hypocoercive linear part is strong enough to overcome the possible growth of the nonlinear part. All right? As long as the initial data is smooth, you can control the growth of the nonlinear part by the decay of the linear part due to hypocoercivity. And the key idea is we have to construct a new Lyapunov function. The Sobolev norm doesn't work. This is hypocoercivity is like degenerate diffusion. You do not get a uniform. This diffusion matrix is degenerate. You have 0 eigenvalues. Some are positive, some are negative, some are 0. But if you want to get a uniform inverse decay, you need a new Lyapunov function, which actually involves mixed XV derivative. It's not just Sobolev norm. But they are equivalent to Sobolev norm. All right? So this is how hypocoercivity for Boltzmann collision operator. So if you take a linearized collision operator, act on H, and take inner product H on L2 space in the velocity space, it gets decay, but here it's not H. It's H perp, which is H minus this projection operator. This is the projection of H into its null space. All right? These are the moments, actually. So you see, this is not H norm. If H norm, you immediately get exponential decay very easily, like in hit operator. But this is the so-called what hypocoercive means. So it's degenerate diffusion. For Boltzmann, actually, we have to use this new norm. It's a weighted norm with this V, where gamma is some parameter in the collision operator. And has to do with whether it's hard potential, soft potential. All right? So actually, this is good enough to get the exponential decay for the linearized kinetic equation. And for the nonlinear part, F, actually we can prove this boundedness. So here, there are a lot of parameters here, all right? So you take L's derivative in X, J's derivative in V, and M's derivative in Z. All right, we have 3 parameters. And then it's bounded by some coefficient, which depend on Z and of this F gamma norm. And then we can bound this coefficient. The coefficient can be bounded by some Sobolev norm of X and V and gamma, all right? And here are some, I don't want to bother to explain details of this Sobolev norm in X, V, and also in the random space. And this is how the Lyapunov function looks like. And it's a little bit concrete. You have L2 norm and in X and V. So those are Sobolev norm. They have this mixed term. To make it a little bit easier, I assume that it's S equals 1. Then you see that this is how the Lyapunov function looks like. So you have this, these are like a Sobolev norm, right? Then you have this actual norm has to do with H per. Then you have this mixed derivative. You have to consider mixed derivative. But if you choose this coefficient suitably, and you can prove this, the first one is positive, second is equivalent to the Sobolev norm. Okay. So once you can prove exponential decay under this Lyapunov functional, then you get the exponential decay of the Sobolev norm because they are equivalent. So this is our result first about sensitivity and regularity. So if you assume the initial fluctuation in the software norm in x and v up to s loading x and v are also the derivative in v, and L infinity norm in z, if that's bounded. Now for incomplete Navier-Stokes scaling, this h and the same norm will decay exponentially with a constant that's uniform in epsilon. And for both L infinity norm in z and soft-level norm in z, hc to power r, r still. For acoustic Euler scaling, I call it Euler because when you do this probability setting, when you don't go to 0, you do not get Euler equation. When you have Euler equation, you have shock and nobody can do anything, even for deterministic form. Nobody can do anything. But because this solution is a small probability from global Maxwellian, when in the Euler scaling, actually in the limit, you get a linear acoustic equation. All right? So that's why I call it acoustic scaling. For acoustic scaling, actually decay is a little bit slower. You have this actual epsilon over there. But these constants are independent of epsilon. So from here, you actually see this perturbation actually decayed. H is random perturbation, but the long time F converges to the decay to the global Maxwellian, which is deterministic, which means this random fluctuation from initial data actually is insensitive. It's not sensitive. This also gives you the regularity. Essentially, the initial regularity in soft-level space is preserved in later time. All right, so this result actually gives you both sensitivity analysis and also regularity. So that's the case for random initial data. What about the random perturbation in the collision kernel? I didn't bother to write down the Boltzmann equation because it takes me half hour to explain the equation. All right, so I'm not going to show you the collision operator. But this is the collision kernel. It's a quadratic, non-local, nonlinear operator, quadratic nonlinearity. But this is a collision kernel, which is completely empirical. All right, so it depends on the relative incoming velocity of two particles, and some other things, which sigma is the relative angle between relative incoming and relative outgoing velocities. And these are completely empirical, so we assume that depends on some random input. And this phi is, with this gamma, well, we can only do the case when gamma is positive, which corresponds to hard potential. All right? So we have to make some assumptions on this B. I assume that is in some soft-level norm bounded. Then we have to use some weighted soft-level norm, which also we use it for the linear transport equation with Jiangguo Liu. Then we get similar decay. Even for the random collision case, we get a similar decay in the long time. Now I'll talk about the numerical analysis. Actually, it turns out we can use also the same framework to study the numerical method, for example, stochastic Galerkin method. You also, now this HK is the case component of the polynomials. All right? Now you have, for this case component, actually now you have a coupled kinetic equation. The left-hand side is decoupled, but the right-hand side is coupled, very similar like a multi-component Boltzmann equation. So this LK and FK couple different GBC modes. And this is standard soft-level norm, weighted soft-level norm. Now we have to make some other assumptions. For numerical method, we have to make assumptions. First, we assume this B is actually linear in Z, all right? Also, we have to assume this fluctuation, random fluctuation in all the epsilon. So this is a technical assumption. At this point, we cannot remove this constraint. So it's small order epsilon perturbation. We also have to make some assumptions on the polynomials. We have to assume this polynomial, the case of the polynomial, if L infinity norm is bounded by constant times k to the power p, for some parameter p. We need this, so the initial data, well, this is actually due to a nice observation by my former PhD student Qi Wang, not Qi Wang Xu, Ray Wen Xu, who's now a postdoc with ITAM. So we need this assumption, so you can choose the initial data independent of the polynomial degree, all right? So it's more robust. It turns out this assumption doesn't work for all polynomials. It works for at least two cases. One is a Legendre polynomial. The other one is Chebyshev. One is for p equals 0. The other one is p equals 1/2. I forgot which is which, but anyway, we have some examples. But not all the polynomials satisfy this condition. Also, for this condition to be satisfied, Z has to be in bounded set. All right, so there's some constraints in this analysis anyway. So this is what we get. First, we have also hypocoercivity for the stochastic Galerkin system. you get this new weighted energy where we had multiplied by k to the q, and q is what this q is you saw in the previous slides. Then actually this numerical energy also has exponential decay. And the fluctuation also of this is the polynomial solution in the same soft-limit norm also has exponential decay in both incompressible Navier-Stokes scaling and acoustic scaling. Well, of course, for acoustic scaling, you have this actual epsilon. So this gives you regularity of the numerical scheme. And we also get the error estimate of Galerkin. So and the same condition for the initial data. So the H analytical fluctuation minus polynomial chaos fluctuation in the same soft-limit norm is you have first your spectral accuracy. So K is polynomial degree and R is soft-limit regularity. Then you have an exponential decay. So here all these constants are independent of epsilon. For incompressible Navier-Stokes scaling, and for Euler scaling, you have this actual epsilon. So this result actually shows that if you use the Galerkin method for Boltzmann, with random inputs for both initial data and the collision kernel, we prove spectral accuracy, and also total GPC error decay exponentially in time. So it's a really long time numerical analysis. How about the variance? So here I actually give you expected value. This L2 is expected value. How about the variance? But if you look at this polynomial chaos expansion, we know the expected value is the first coefficient. The variance, well, this is still another typo, k should be from 1, is summation for all the L2, summation of the square of this. Because our framework is built on L2 and Sobolev space, so by Passoir identity, actually, in the method, actually, our result extended not only for expected value, because we do in the L2 framework, we also give exact same accuracy and decay estimate for the variance. All right? So it also gives you information about the variance, exponential decay of the variance. The method actually, the framework is general, because it's general framework for deterministic problem. So it works for essentially all linear and nonlinear collision kernel equations. And also we are able to also do it for non-collisional kinetic equation. For example, Bloch-Poisson Fock-Planck equation, which joint works Yu Hua Zhu. And so this is the conclusion essentially. We have developed in the last few years stochastically from many different kinetic equations, including Boltzmann, Landau, two-phase flow, where you couple incompressible Navier-Stokes equation with kinetic equation. We also developed some other issues like fast algorithm for collision operator and so on. We also had a new paper on Landau damping, which is another work that won Fields Medal for Villani. So if you have Bloch-Poisson without collision, it turns out which Raven Shu, at least for a special case, we can prove the Landau damping can also survive. The regularity of Landau damping, which allows requires solution to be analytic, we can prove with random perturbation that it remains same analytic framework. Well, we haven't got to the point of Moholt-Villani techniques. We used the technology before their Fields Medal work, but we try to get to there with real ones. So essentially the message is that for kinetic equation, I can use, other than this, you can extend the deterministic AP work to stochastic setting. You can use hypocoercivity to analyze this random kinetic equation to get a lot of results, regularity, sensitivities, even for long-time behavior and numerical methods. And the take-home message is that actually kinetic equation has good regularity in the random space, which makes it a very good problem for UQ. And also you can develop very nice numerical theory, because a lot of good important theory for in the deterministic framework. It can be extended in a very straightforward, or not straightforward, but in a nice way to a random problem. And also I find that many kinetic equation has a lot of things in common with uncertainty problem that people have been studying. So there are a lot of theory from kinetic ideas can be very useful, for example, mean field approximations, moment closure. And people in UQ community also do these kind of things to reduce the dimension. So I find the marriage of two areas can be very fruitful, all right? But another thing is that there are a lot of open questions. I mean, there are very few works. So, for example, how do you do boundary conditions with resonance? So, from my own experience, I really find kinetic is a very good problem for UQ. So as Chengdu invite people to work on non-local problems. These are also non-local problems. So I invite young people if I mean, this is a wide open areas, a lot of interesting problems. For that, I stop here. Thank you.
Thank you. Do we have any questions or comments for Shi Jin?
That's it.
I'm Siddharth Mishra, and my question to you is, I did not get, is your Navier-Stokes Boltzmann passage asymptotic preserving, or is it not?
Yeah, it is because we get the estimate uniform in epsilon, so of course it's asymptotic preserving.
But the problem then is your...
This is asymptotic for the stochastic Galerkin. I didn't talk about spatial time digitization. This is only for stochastic Galerkin. So you see that H minus the polynomials of degree K, the area is bounded uniform epsilon with a spectral accuracy. It's uniform spectral accurate in epsilon. So this guarantees the stochastic Galerkin is AP, right?
The problem is that somehow you have this insensitivity to random initial conditions as a consequence, right?
Under those technical assumptions, it's insensitive. But if you remove those assumptions, we don't know. Yeah.
Navier-Stokes is extremely sensitive to randomness in the initial conditions. So that's why I did not understand how these assumptions play out.
Here is a hypocoercivity. So we consider solution is a small perturbation of a global Maxwellian. For global Maxwellian, it's e to the minus b squared, right? So that's not it's a rather simple case. But that's how far we can go, because that's how far the deterministic framework has been going. Nobody can prove away from global Maxwellian, you start develop a shock. Nobody can do anything at a lake level for fluid dynamic problem. If you can do it, you get field metal, I'm sure.
I can't do it.
Yeah, so that's technical assumption.
Okay.
I mean, we can only do it in the perturbable setting, sort of weakly nonlinear. This theory only works in the weakly nonlinear regime. Unfortunately, that's how far, even for deterministic framework, that's how far we can go up to date. Yes?
Alfio Quarterone from Milan. So it might be a related question somehow. It's a curiosity, actually. You are plugging your stochastic dependence into the equation through the polynomial chaos, and you recover spectral accuracy. Although the underlying equation is, say, the nonlinear case is not smooth in the Sobolev scales.
Yeah, that's right. That's why it's Sobolev norm.
All right.
If you have shock, you cannot use this norm. Yeah.
Okay.
Sure.
So, well, I mean, I'm just wondering where you, how you can somehow avoid this mix-up between the dependence on Z, dependence on the, say, the stochastic part, and the dependence on the spatial coordinate. How can you be preserved from somehow destroying or reducing your smoothness in the stochastic part?
Well, the theory only works when solution is smooth. If solution non-smooth, that's why we need a numerical.
You mean the solution of the deterministic equation?
Yeah.
All right.
If it's solution not smooth, you have to do numerics to quantify uncertainty. Here, if it's smooth, we have a mathematics theory, rigorous mathematics theory to do this numeric analysis. But this is not the end of the UQ. This is the beginning of the UQ, because when you have shocks and things like the pictures, that's the area where this analysis doesn't work. And we need a numerical UQ, right? So there are a lot of open questions. If you look at this earlier picture I showed you for the shock tubular, I mean, of course, our analysis doesn't work in this case. And you have to compute, numeric compute, to understand what the possible deviation is if you have a random inputs in the initial data or equation of state or collision kernel.
But can you envisage using in those cases some kind of smoothing or regularization or say numerical flux in a broad sense also for your stochastic part?
There might be, for example, this random dependence, there might be some velocity average. I mean, Aitan asked me that question. I don't have an answer yet. This is the area where it's wide open. There are more questions than answers. All these series has this limitation because it assumes solution is smooth. You can use Sobolev norm. And for non-smooth, the only good attempt is Depris and Patton, where they do scalar. They use kinetic formulation for hypothetical conservation law. They use what they call a kinetic polynomial. It's not a kinetic polynomial chaos, which is beautiful theoretically, but they confess nobody's going to use that for computation. Because there you have to use L1 framework. Once you start to talk about shock, and all this L2 or Sobolev norm, you cannot use it anymore. Yeah, so this analysis, although very good, important, you can do a lot of things, has its limitation. That's why this is beginning of UQ, not the end of a kinetic UQ, because for this problem, you have to do numeric simulation. You have to have a good method. Actually, this is the problem that's very hard, actually. If you do stochastic Galerkin for OLA, you get you lose hypocoercivity, which is very similar to if you close the Boltzmann by grad certain movement, you also lose hypocoercivity. There are a lot of problems that's very similar, which make these two communities. I think these two communities we have to talk to each other, because there are a lot of similar challenges, actually. Yeah.
Thank you.
Did you have a question? No. Okay, let's thank our Professor Jin one more time. Thank you.